Hello, good evening.
Sir, good evening, sir. We'll start in 5 minutes, sir.
Sure, I'm ready. Just let me know whenever you are.
Yes, sir. Sure, sir. Thank you, sir.
Sir, shall we start, sir? Meanwhile, they'll.
Sure, absolutely. I'm ready.
Thank you, sir. So, good evening, dear participants. Welcome to AICTE sponsored ATAL FDP and Key Technologies Enabling 5G, Day 2, Session 3. So, it's very fortunate and privileged to have such a great speaker for our session. So, now I would like to request Mrs. Monica ma'am to introduce today's esteemed speaker for this session and introduce to the participants. Ma'am, over to you.
Good evening, everyone. I once again welcome all the participants for the second day online AICTE sponsored ATAL Faculty Development Program on Key Technologies Enabling 5G, organized by Department of ECE, BITS, Narsanpet, Warangal, Telangana. Myself, S. Monica, Assistant Professor of ECE Department, BITS. I feel it's a great privilege to introduce today's session resource person, Dr. A.G. Krishnakant. Dr. A.G. Krishnakant is the founder and CTO of Moss Art Labs, a VLSI edutech company founded for upskilling ECE and EEE students in the field of semiconductor technology and chip design. He served as the director of analog mixed signal R&D at AMS Semiconductors. He is an IEEE senior member and currently the vice chair for IEEE CAS EDS Hyderabad chapter and is frequently involved in delivering technical lectures at various universities. He received his PhD from IIT Hyderabad. He finished his BTech and MTech from IIT Bombay with specialization in microelectronics. He was awarded with President of India Shankar Dayal Sharma a gold medal and IIT Bombay Student Roll of Honor in 2002. Analog IC design is his passion, and his specialization includes sensors and sensor interfaces, high performance analog signal processing, power management for automotive and consumer semiconductor IC design. He worked earlier with Texas Instruments Bangalore and Qualcomm Logic Hyderabad, leading the analog IC design teams. He is an adjunct professor at IIT Hyderabad and Digital University Kerala. He is on academic council and BOS member at several universities. He has 13 patents and 11 IEEE publications. He is an associate editor for TSAS2 for the academic year 2024 and 25. Thank you, sir, for spending your valuable time to share your thoughts on this session. Now I hand over session to Dr. A.G. Krishnakant, sir. Thank you, one and all.
Yeah, thank you, ma'am. Am I audible?
Yes, sir. Yes, sir.
Yeah, and is my screen visible here in the
Yes.
presentation mode?
Yes, sir. Yes, sir.
Okay. And how much time do I have?
Sir, it's your wish, sir. Up to 1 hour or more than 1 hour.
Okay, up to 1 hour. I'll keep that in mind.
Okay.
Okay, so let me start. I'll stop the video because so the bandwidth issues we may have. So just will stop the video.
Okay, sir.
Okay, first of all, thank you for inviting me for this FDP to interact with the audience and share some of thoughts about research geometry and circuit systems. Since this is more related to a 5G technology, I have picked one specific domain which is evergreen in terms of the any technology that you pick, 4G or 5G, which is basically the power management part of the 5G technology. This is what I will focus on with a brief introduction. And once again, thank you for having me here. So let's start with the presentation. Okay, so as a quick background, we basically have seen like 4 industrial revolutions. The first one is, of course, Industry 1.0, where this was about running things on steam and water power. Then we got Industry 2.0, which was about mass production, assembly lines, and mainly using electric power. With the current being available, people are able to build assembly lines. That was Industry 2.0. Then until recently, we had Industry 3.0, which is more about automated production, computers doing the job, IT systems where you kind of code things to happen the embedded systems became very popular here, and you use software to control hardware, and thereby robotics also came into play, where you were able to do a lot of automated tasks without using human involvement. Now we are currently in Industry 4.0. This is more about really the smart factories, the autonomous systems, the high-speed connectivity, IoT, machine learning, and so on. And this is where a 5G technology clearly plays a role, because in Industry 4.0, connectivity is absolutely important. And that's why the sensors and connectivity, essentially, these are the heart of Industry 4.0, which is where we are. Okay. Now, I just picked this as one of the RF front-end structure for a typical 4G and 5G front-end. And I'm sure in this course of FDP, you would hear a lot more from the speakers on several topics, like you have a transmitter, you have a receiver, there's power amplifier on the transmit power, there's a receiver on the LNA path, which needs to be low noise, and then you have a lot of filters, rejection, then you have antennas, and which would be tuned to a certain frequency, and then so on. So all of these. So my scope of the talk is none of these, but mainly focused on the top, right? So whichever technology you pick, you would need the whole technology or this front-end architecture, be it 4G, 5G, and as you move towards 6G, right? You need to do faster and faster data transmissions. And as you would know, a faster data transmission also means significant power consumption. So, and some of these, as you go to lower technology nodes, this entire system on chips are now built with lower and lower voltages as well. So you can go down to 1.5, 1.2, and now even there are processors that are now being built at 1 volt, digital IC, and then the analog of the RF front end still remains probably at 2.5 or 1.8 volt. So you clearly need from a basic power source. If you look at a mobile phone, you have a lithium-ion battery which is powering from, let's say, a 4.5 volt when it is fully charged, and then 2 volt when it is coming low. You can also have a USB power there, so now I think the connectivity is not only limited to consumer goods; it is also now entering into automotive. Every car now has connectivity, mobile connectivity, where you have Bluetooth, you have wireless LAN. People keep advertising internet inside cars and then so on. So all of these would mean not only are these transceivers becoming important in a consumer segment, but these are like mobile phones that we all know. It is also becoming important in automotive segment. So I thought, since this is a cool combination to really understand power management circuit, but also in the context of automotive. So this is where my subsequent slides will be focused on. We want to understand how do we really design automotive power management circuits that are really supplying these high power consumption. Some of these transceivers would need hundreds of milliamps of current. And my talk would primarily focus on building power management ICs, building these DC-DC converters and LDOs, which can really supply a high current. And this specifically in an automotive domain, because this makes it a very interesting combination in terms of the application area. Okay. So with this background, I would like to focus on just let's understand a bit more about what is special about an automotive design, or what is so special about designing something for automotive compared to a consumer or like a phone or a car, right? So typical automotive PMIC requirements would mean the several things. If you look at automotive battery, we can have a lead acid battery, which is about 14 volts when it is fully charged. Or you can have a lithium-ion stack battery for all the EVs, where you can even see that the lithium-ion stack is going to 100 to 300 volts right now. For today's presentation, I would focus mostly on the lithium-ion battery cell. On the lead-acid battery, where the input voltage can be anywhere between 4 volts to 18 volts in the entire operating range, and there are challenges when you do a load dump or when you do a battery cranking. Then the voltage can go as high as 42 volts during a load dump, and even higher. So this would mean the integrated circuit that is now being used to power convert this. So you can think of it like, if the battery power is like 4 volts to 18 volts, and a 5G transceiver needs about 1.2 volt for digital, 2.8 volt for analog power amplifiers, then you would need multiple voltages to be generated from this battery power supply, right? And that is the challenge we want to look into. How do we efficiently generate multiple supply voltages from a known battery source reliably, efficiently, and in a cost-effective manner? This is the problem statement. So typically the output voltages that this power management IC needs can be anywhere between 1 volt to 5 volts. Let's say 1 volt if you're talking about the digital core of your transceiver, or you can have 2.5 volt or 2.8 volt if you're talking about the transmit side, or you can have more if you're talking about a microcontroller, a graphic processor, or an embedded system. You can have multiple voltages like 3.3 volt or even 5 volt sometimes in automotive. So these are the output voltages that needs to be generated from the power supply, which is 4 volt to 18 volt. The load currents can be anywhere between 5 milliampere to 5 amperes. So very, very power hungry circuits. As you go to higher and higher speeds, you can have pretty high currents as well. So for our scope, we will limit it to a few amperes, like less than 1 ampere current, because we don't want to get into the power MOSFET technology. And in fact, for the EVs, they are also using the currents which are going as high as 100 amperes to do the motor drive for its own electric vehicle. So that is not the scope of this. We are looking at power management ICs mainly supplying tens of milliamperes all the way to hundreds of milliamperes for a typical transceiver. Okay, and based on where the transceiver is put, the temperature range that these automotive PMICs should handle are anywhere between -40 to 150 degrees centigrade. Now I'll come back to this topic of why we need 150 degrees centigrade for our circuits a little later when I come to the thermal dissipation. Then, of course, from connectivity side, you need a lot of conformance requirements. So these are typical automotive standards, maybe not relevant to a 5G topic, but just wanted to highlight here that the ESD requirements are very stringent. You need EMC requirements. The 5G transceivers have fast switching, so you have a lot of emissions that are coming into play. So also the PMIC DC-DC converters, they are also switching, so they can also give a lot of emissions. So it is important to meet a certain EMC requirements, which are part of your conformance, LIN, CAN, or FlexRay conformances, and it's important to know. Plus, for automotive PMIC, you also need design for test, manufacturability, quality requirements, because the IC, when designed in, needs to work reliably for 15 years, right? It has to meet a certain lifetime requirement, because we probably change mobile phones, let's say once in 3 years or 5 years, but we don't change cars often. So the same circuit when designed in a mobile phone versus the same circuit when you design in an automotive mobile has a different lifetime requirements, different quality requirements, different reliability requirements. So all this starts from the design itself. So you need to have more margins of the design, more robust simulations to make sure that the quality and reliability requirements are met. In addition, a lot of these thermal, because these are high current LDOs, right? You don't want to burn, if you have a short loss of supply or loss of ground, we don't want to burn the system. So we need thermal shutdown, we need over voltage protection, brownout protection, over current protection. So all of these safety features needs to be incorporated in the chip design itself. Okay? So this is how typical automotive PMICs requirements look like. Now, let's understand a bit more on the automotive battery. Okay? So typically a fully charged lead acid battery can be as high as 14 volts. So what is the big deal about it? The big deal is that when you look at the transients during a car operation on a 14 volt battery, you would see that you would be surprised to know that during these are phenomena like in a load dump, failed regulator, an inductive load switching, or an alternate field decay, ignition pulse, harness coupling, ESD. Let's say you suddenly crank your engine or you turn on your AC. All of these will lead to very high transients on this 14 volt battery. And you can look at the voltage level here. You can see that this can go to 125 volts for about 200 to 400 milliseconds. Then if there's a failed voltage regulator, you can have the voltage go to 18 volts. And then some for a short switching at 320 microseconds, you can have voltage going as high as 80 to 300 volts. So a 14 volt battery typically sees all of these extreme transients in the chip. So we take help of some of the external protection, like transient voltage suppressors or snubber circuits, but the chip that we design needs to meet at least the higher voltage requirements and should be robust to some of these high voltage requirements, even though it is a 14-volt system. So now, when we talk about the integrated circuit environment, what are the typical variations that we need, or the external influences that we see in a chip, in a integrated circuit environment? So two main things. One is the environment itself can change. And when I say environment, this could be a voltage. So one, of course, the power supply voltage is changing. There is probably power supply noise that you see also on the voltage. You may have a ripple on the voltage. Then, of course, the temperature is changing. So your car, the automotive PMIC, or even look at a transceiver, a 5G transceiver needs to work at extreme temperatures, like, minus 40 degrees C in Siberia. And also it should work at, 50, 60 degrees C on the Thar Desert, right? Extreme temperatures. Of course, with the self-heating, it's going to be even more worse. The engine also gets hotter. So when you look at the engine temperature, this is even going as high as 125 degrees centigrade at the ambient. And then, of course, electromagnetic compatibility. This is the reason, for those of you who don't know what EMC is, this is basically the electromagnetic compatibility. This is the reason why when we get onto a flight, the air hostess asks us to shut off our mobile phones, right? Because the electromagnetic emissions from our wireless transceivers, especially with 5G coming into play, it's going to be even more stringent in terms of EMC. So that's why it is very important to understand the EMC and ESD and build this robustness in the circuits. So yeah, a little bit on this. So we have, of course, we have ambient temperature range, but then you also have an on-die temperature because of self-heating of the chip. So when you have a lot of current that your chip is burning during high-speed data transmission, now, especially you look at power amplifiers, they really consume lots and lots of power. You have all these class A, class D amplifiers, which are extreme, which have to throw a lot of power, and this will generate a very high temperature on the chip. So the power management circuit needs to withstand these high temperatures as well. Okay? And based on the application, you can have commercial application, maybe let's say minus 10 to about 70 degrees is okay, whereas industrial application needs to go from minus 40 to 85. Military applications need minus 55 to about 125, and then you pick some of the technologies for extreme military grade, like minus 55 to about 300 degrees centigrade. So based on your application, we have to pick the appropriate semiconductor technology to support these application requirements. So in our case, we want to limit it to about minus 40 to 125 degrees centigrade, because this automotive application typically these things are in the dashboard, so it is okay to limit to minus 40 to 85. Now, the second important point, which is most often neglected, but a very, very important factor in designing reliable circuits, is wear out. So what is wear out? So the circuits, like human beings, they also age with time. So this means whenever you design something at t equal to 0 today, the circuit looks very good. I take an example of mobile phone always. When you buy a new mobile phone, the battery charge looks great. The touch screen is very responsive. Your audio, your screen, everything looks great. But as you spend 2 or 3 years with this phone, you start seeing that battery life is not so good. Touch screens have become less responsive. The processors have become slower. So this is a true phenomena. It's basically because of your wear out. So semiconductors do change their properties, or these transistors, they become worse, primarily because transistor changes over time as they wear out, mainly through the hot carrier injection effects, the negative bias, temperature instability, or time-dependent dielectric breakdown. These are some of the phenomena which leads to change in threshold voltages. So the threshold voltage of the transistors, they degrade with time. So whatever we designed at t equal to 0 may not be the same performance at t equal to, let's say, 10 years or 15 years. And this is where, as designers, we have to be aware of this fact. Now, we cannot test something for 15 years, right? There's no way we can do. But where we use is the reliability models, where we say, if a circuit works at elevated temperatures, like if you have to meet 85 degrees centigrade, push the temperature to 125 degrees centigrade and make the circuit operate for 1000 hours. Now, you can build a model and then say, if my circuit operates for 1000 hours reliably without much degradation at 125 degrees C, then the circuit will operate for, let's say, 10 lakh hours or 1 million hours at 65 or 70 degrees C. So this is called Arrhenius equation. It kind of builds an extrapolated model in terms of time to estimate the lifetime of a circuit. So basically you stress the circuit beyond its operating point in terms of temperature or supply voltage, measure the performance with a limited time, and now extrapolate and say, okay, at this extreme temperatures, if my circuit can withstand X hours of time, then maybe at room temperature, it will withstand 15 years, or at elevate 60 degrees, it will withstand 12 years. So that's how you build models. So you do accelerated life tests to really confirm that the performance after aging is still within your limits. Okay, so in short, the environment is changing, so nothing is constant in an IC in absolute terms. But we still use the fact that two transistors under similar conditions behave similarly. This is the whole concept of matching. And as designers, we always need to make sure that two matched transistors, they are put in a similar condition, always, in the design and also in the layout. Now, let's come back to, guys, still see, let me hide this, hide the panel. Okay, still not going. Let me. Good. Okay. So do you see? Okay, I guess you're seeing my screen, right?
Yes, sir. Yes, sir.
Okay. So now in power management IC, before we go deeper into DC-DC converters, let's just understand what are the different fundamental IPs, since we also want to talk a little bit about research opportunities, right? For this, so mainly from power management perspective, the source of power, you can now pick either a lead acid battery or a lithium ion battery. And for a lithium ion, one of the many important topics is that you have these stacks of lithium ions that are stacked to really generate this 300 volts or 100 volts. And you would have seen it's a big deal now with you start seeing these EV scooters failing these days, and mainly that is because the battery management is not good. So so the battery management of these batteries are a big research area where a lot of people are working on to efficiently estimate the state of health and state of charge of these batteries, and to reliably monitor the battery so that no fault happens. Then there is also, at a smaller scale, people are also looking at alternate sources of power because of the sustainability topic, where you can have solar, wind, thermal vibrations, all of these now used as a source of power. And this comes to the topic of energy harvesting. So while this may be still a far-fetched dream to run a 5G transceiver through some of these, it's still a goal that people target. How low can you go to the power, and how high can we harvest energy from our sources of power? And then while we have RF harvesters, we also want to build on-chip transformers and rectifiers to be able to convert an AC power or an alternating power into a DC source through these rectifiers, which can power our ICs. Then, of course, while we are converting the power, it is important to take care of power efficiency, because power efficiency is very important, since, of course, this means that you are draining out the battery quickly if you are not efficient. Two, this also means that you dissipate a lot of heat. All the loss of efficiency should be dissipated somewhere, right? Energy is conserved always. So if you're delivering something to the load, whatever you're not delivering to the load is now burnt on the chip, and this means the chip temperature increases. So that is why it is very important to always keep the system or design the system in the maximum power point transfer, where the efficiency can always be maintained high while you're transferring the power to the load. Here we come to the point of switching converters, which are extremely popular, DC-DC converters, which are very efficient, especially when you have high currents like in a transceiver. People mostly use DC-DC converters. And here you have several varieties of converters. Now there's buck converter, where you're converting from a higher supply voltage to a lower supply voltage. Typically for 5G transceiver case, it is usually a buck converter that is being used, because the 5G transceiver is operating at a lower voltage, whereas lead acid battery is at 12 volts. So you have a buck converter which is stepping down the voltage efficiently. We can also have boost converters where this is stepping up the voltage. As an example, if the battery goes to 4 volt, but you still need to deliver 5 volt to power amplifier, right? So now you need to boost the voltage. And if your battery can go between 4 volt, 18 volts, and your output needs to be 5 volt, right? Then you need a buck boost. So where when the input voltage is high, you buck the voltage. When the input voltage is lower than output, you kind of boost the voltage. So it's a buck boost converter. Then there are other varieties like SEPIC, flyback converters. All of these are possible. So you can see that DC-DC converter itself has many varieties of power converters, which can be studied in a lot more detail. Then in terms of number of components we use, typically each power converter comes with an inductor, external inductor. You would have observed that in my first slide as well, when I showed the LTE front end. These high current converters always need an external inductor, which is the order of few microhenry. So in order to save some of these components, there is a class of converters called CMO converters. This is single input, multiple output converters, or single inductor, multiple output converters. So you take one input, one inductor, and then you should be able to supply multiple outputs, like 2.8 volt or 1.3 volt. Then you also have a class of MIMO converters where you have multi-input, multi-output. So you can take the input from solar, wind, thermal, lead acid, and all of these added as energy onto one single battery source. This is a multi-input and multi-output converter. Okay, once we have a power efficient systems, it's important also to understand that DC-DC converters are intrinsically noisy because they are hard switching devices. Now you turn on the power FET either to 0 or to 1, which means you fully turn on this device or you shut off the device. So it's a hard switching device. So even though we have an external inductor and a capacitor to filter out, there's still going to be a ripple. And some of these ripples are extremely problematic, especially for building low noise amplifiers. So if you have your receiver, a 5G transceiver receiver, right? The low noise amplifier needs to have much lesser power supply noise so that you can reliably extract this weak signal on the receive path. So you may need to sometimes employ low dropout regulators to clean up the power supply. We could fire it directly. Some cases you can feed the DC-DC directly, but for sensitive regions, we may want to have a low dropout regulator. And this can be a wide band based on the signaling that we're doing, or an on-chip or an ultra low power LDOs, right? And then, of course, in terms of choice of technology, CMOS, which is still the mainstream for low voltages, and then high voltage CMOS, where you can build extended drain transistors, which can withstand all the way till 50 volts and even sometimes 120 volts. BCD is quite popular for high voltage designs. And then for electric vehicles, we have gallium nitride and silicon carbide, which are very robust, and they can help build these power MOSFETs, which can be used as for a power converter drivers. So you can see that just looking at the power management IC domain, you can now have several variants, flavors, and sub flavors of all of these. And each term here is a topic in itself. There's a lot of research papers and journals that get published in each of these. Okay, now let's come back to the automotive PMIC topic now that we understand the challenges. While we want to design a CMOS DC-DC converter, we have to first understand what are the technology requirements. Like the first green region shows that when the supply is 6 volts to 18 volts, this is the functional range. So the PMIC, or the power management integrated circuit, needs to operate always in this range. But during some transients, the supply voltage can go to 18 volt to 42 volts. So we need to somehow limit the power supply voltage during these transients to, let's say, less than 42 volts. And that is needed because the SPICE models of these transistors typically are valid only till 50 volts. So that means the fab guarantees that as long as the VDS is less than 50 volts, then the transistor operates for a lifetime of more than 15 years. So the SPICE models are mainly valid in this case. So beyond 50 volts, we still need to have ESD region. So this means below 50 volts, you can still be functional, or you can operate at this for a smaller lifetime. But beyond 50 volts, you still need some place where you can design the ESD structures so that it doesn't interfere with your functional case, but then it triggers whenever you have an ESD strike. Okay. And then after 60 volts, you have a transistor breakdown. So this is where you have a snapback and relay transistor breaks down. So now you see the challenge to design a circuit that is operational between just 6 volts to 18 volts. You have to pick a 50 volt transistor simply because you have all of these things that you need to take care of. So this is the first challenge when you design automotive PPICs, deciding the optimal process technology to limit the overall design consideration. And you can also see that for based on where the ECU is located, right? ECU means electronic control unit, or this DC-DC converter is located. If it is in the passenger room or inside the car, then you can have under the dashboard a temperature which is minus 30 to 85. But if it is close to the engine, in the front compartment close to the engine, then your ECU box can be much hotter, all the way till 105. Under the hood, this can go to 125. And when it is connected to the engine, right, as an example, airbag deployment or transceiver where it is connecting. Here you can see the temperatures can go as high as 175 degrees as well, which is very, very hot for the circuit to operate. So these are the challenges that we see from technology perspective. And the SPICE model or the process development kit that we use to design these transistors not only should withstand high voltages, but it should also withstand 150 degrees centigrade at least a minimum temperature under which the models are accurate. Okay, let's come back to, I want to give an example of a reverse camera PMIC just to understand what are the challenges we would face while designing a power management IC. So let's assume we have a battery voltage of 6 to 18 volts, and then our RF transceiver needs multiple supply voltages. Like let's say a microcontroller needs 1.8 volt, and then the power amplifier needs, let's say, 3.3 volt, and something else needs 5 volt. And something else needs 2.5 volts. So these are the voltages that needs to be generated from the battery voltage. Okay. So now you can see that this can be represented as, okay, so this is the math problem. So if you look at a small math when we do, right, what is the load across the 5 volt transistor? What is the efficiency of DC-DC converter? Efficiency is, maybe let me take a pointer. Okay, so efficiency of any system is output power. So output power divided by input power, right? This is the efficiency. So if both are same, then it's 100% efficient. But then if output power delivered is smaller than input power, which is typically the case, then the difference between input power and output power is the loss. Okay. So now output power is also same as, let's say, V out dot I out. So this is the average. And this is input power is same as V in by I in. Okay, so now for this DC-DC converter, we can calculate the efficiency. Typically, from experience, these DC-DC converters usually have the efficiencies anywhere from 85% to 90%. Okay, based on the output voltage that this is delivering. So now let's take a pessimistic example as 85%. Now I can calculate the power dissipation or the self-heating of the chip, where the power dissipation is output power, which is 600 milliampere. Why this is 600? You have 150 from here, another 150 from the 3 LTOs, right? So the total load current from 5 volt is actually 600 milliampere. So this is the 600 milliampere. So the output power consumption is 600 milliampere into 5. This is roughly, 3 watt, right? 0.6, so 3 watt. Okay, so now if you know that the efficiency is only 85%, this means the power dissipation because of self-heating, the wastage is, if you do a simple math, you will realize that the wastage is coming out 0.53 watt here. Similarly, when you do for all the LDOs, you will also see that each of these LDOs, based on the output voltage, the wastage is going to be 5 volt. So in this case, for LDO 1, the supply voltage is 5, the output voltage is 3.3. So the wastage is 5 minus 3.3 to 150 amps. Similarly, for LDO2, it is 5 minus 2.5, basically the dropout into the output power. That is the power that is wasted on the LDO. And so these are all the numbers that you would end up with, 0.26 watt, 0.375 watt, and 0.48 watt. If you add all of them, you would get about 1.64 watt. What does this mean? To deliver this load current at different voltages, the self-heating or the power wastage of the chip is simply 1.64 watt. And each package has a thermal resistance. So this means what is the amount of temperature increase for every watt of power dissipated. So typically based on the package, you can have this, you get the number from the vendor. This can be anywhere between 35 degrees C for larger packages, and it can go as high as 50 degrees C or 70 degrees C per watt for smaller packages. So this essentially means that if you have 1 watt of power dissipated on the chip, then the chip temperature will increase by 35 degrees. Okay. Now, we also know that the SPICE models are accurate only till a junction temperature of 150 degrees. This is our hard limit, because anything more than this means that we cannot guarantee that this car will be reliably working for 15 years. So this is a constraint on the SPICE models. Now, what this means now is the maximum temperature can be, the self-heating will be 35 into 1.64, because we have 1.64 wattage of power and it is 35 degrees centigrade per watt temperature. So you get around, roughly you get to about 58 degrees centigrade as the self-heating. So this means the maximum application temperature or the ambient temperature cannot be more than 92 degrees. Why? 92 degrees is the maximum application temperature, and then you have additional 58 degrees of self-heating that will get to 150 degrees centigrade. So this is how you calculate how to be sure that you are able to meet an application temperature. Let's say if you want to design an engine, something close to engine control, right? Then this won't work, because you will need to limit the temperature to 92 only. So maybe only at the on a dashboard applications you can still make it work, because dashboard is less than 85 degrees. So before designing any power converters, it is very important to understand and make a thermal calculation of the application. This will tell you exactly what is the maximum application temperature that the chip will support. Okay, so now for a rear view camera PMIC, when we looked into it, some of the existing PMICs and hybrid regulators had a couple of problems. One, they had bulky external components. So this means you had a lot of huge inductors or huge capacitors. And then some of the transceivers need multiple ICs for each voltage. So there was no integration done. So it was a challenge also to generate all the supply voltages from a single chip. And then most times these DC-DC converters are optimized for highest load current only. And typically when you look at it, right, when you're trying to operate a power amplifier or when you're trying to operate a 5G system, it's not only the peak power, but you can also have only the receiver turned on or only transceiver plus receiver turned on, and then so on. So you have to optimize the system for entire load current, not just the highest load current. And last but not the least, most ICs do not cater to 150 degrees requirement, because we have seen there, unless you have 150 degrees centigrade with the self-heating, you will not be able to meet the 85 degrees C. So this was a good research problem for us to solve. And this is what we started looking into it. So now, what is the motivation to go for automotive rear view camera? I mean, these days you see that a rear view camera is now part of every car now, because US legislation had made it mandatory since 2018. Now even in India, a lot of manufacturers have rear view camera there. It's basically for passenger safety and driver assistance systems. Yeah. So efficient power management ICs are needed to really convert a noisy battery voltage into fixed output voltage. So these are, all these ADAS applications, lane change assist or driver authentication, all of these need the ADAS systems, and the power management ICs play a big role to supply the respective power to these ADAS. So that's basically the reason why we need to build this application. Okay, so now coming back to our target, our unit has, so this is about identifying the requirements, electrical requirements. And those of you who are working on your PhD or you're working on some research work, this is a very important part of it, because every time you're working on a problem, you have to draw the boundary conditions. What exactly are the conditions that I need to design for? They should be very clear, because you can't start doing a generic design, right? You have to fix your boundary conditions and then design the work. So here I've tried to limit the whole boundary condition and say, okay, my supply voltage variation is this. Then I need 3 voltages or 4 voltages, 1.8 volt, 2.8 volt, 3.3 volt, and these are my load current requirements. I need to maintain my ambient temperature of 105. Now you see 85 is not sufficient. I need to go to 105 degrees, but still maintain the temperature less than 150 degrees centigrade. And number of external components should be minimized because this is space and this is cost and also weight. And I need a system efficiency of greater than 60% over the entire 95% of the load current range. So these are my target requirements to design the system. So in short, the way this power management unit would look like is getting from the V supply of 6 to 18 volts and delivering these 4 supply voltages to some of these systems where you have image sensor or GPU, or it can be your transceiver, 5G transceiver, or a 32-bit microcontroller that's sitting there in the application. And of course, the cadence simulation should consider all our process corners, CMOS, typical verse speed, verse power, resistor, capacitor corners, bipolar corners, all of them are extremely important to design the entire chip. Okay, so now let's understand the DC-DC plus LDO trade-offs. Now, step-down ratio is a very important parameter to understand while designing DC-DC converter. And step-down ratio is basically the supply voltage divided by the input voltage or the supply voltage divided by your output voltage. So higher step-down ratio means that your DC-DC output voltage is much slower, much smaller than your input supply voltage. And typically, when your step-down ratio is high, the efficiency of the circuit is limited to about 75% for these high voltage converters. Of course, you can say by better design, I can go to 80% or 85%. This is possible, but as a thumb rule, you can pick this number for an integrated chip, right? And this is these numbers are also thumb rules, and you can have based on your R-on of the transistor, based on how much size you can afford in the chip. These can be optimized, and we can go even push it even higher. Now, for high voltage DC-DC with moderate step-down ratio, as an example, you have 6 volts to 3.3 volts, or 6 volts to 5 volts. You can have efficiency as high as 85% typical, and which can go even to 90%. For low voltage DC-DC, this means you have a 3.3 V supply is about 3.3 or 5 volts, and then you're going down to about 1.8 or 3.3 volts. So you can use a 3.3 or 5 volt transistors, which give you a much better R-on. So the DC-DC efficiency can be as high as 90 to 95%. So these are how you can use these numbers to model the system. And I will show later how we decide the architecture for this problem. Keep these numbers in mind. And with that, then we can start building the architecture. Now, as a quick trade-off between DC-DC converter and LDO, DC-DC essentially has a higher efficiency because the energy is stored not in passive components, but in active components like inductor and capacitor. So they are lossless. So your efficiency is high and supply dependency is not so much. Whereas for an LDO, because this is linearly regulating the pass transistor, the efficiency is poor because in LDO, it is simply efficiency is output voltage by input voltage. Output ripple is high because you're doing a hard switching in DC-DC converter. Whereas LDO, the output ripple is very small because the gate automatically adjusts to the power supply and then giving you clean output voltage. Now for DC-DC, you would need off-chip components, be it inductor, be it capacitors or Schottky diodes. Whereas for LDO, you can limit it to capacitor. And in some cases, you can even do with on-chip capacitor instead of an external capacitor. So LDOs typically need lesser off-chip components, so lesser weight, but they are poor in terms of their efficiency. So when we started, so given that we wanted to design the choice was to say, okay, let's design the most efficient system. So, and for efficiency, we know that we need all high voltage DC-DC converters because we need the power 12 volt and going to about 2.5 volts and a 1.4 volt, right? So this is the first choice would be to keep all of them as high voltage DC-DC. Now with high voltage DC-DC, you know that the efficiencies become poor and also you would need a lot of silicon area. So what we thought was, okay, let's improve this further and then say, let me put one high voltage DC-DC, but then have multiple low voltage DC-DC converters. Why? The high voltage DC-DC can be down converted to a lower voltage, like instead of directly taking it from the power supply, right? You can put one high voltage DC-DC down converting it to about 3 volt. Now from this 3 volt, you can generate all the required voltages. And here you can use low voltage NMOS transistors. When I say low voltage, 3.3 or 5 volt transistors. So which has much better efficiency. So this could be one easier way to improve. Now, you see that these are still DC-DC converters, which means you need a lot of external components there for both for high voltage DC-DC and low voltage DC-DC. And in addition, we know that the low voltage DC-DC, you still have a lot of output noise based on the switching. So we need a cleaner supply. For example, your receive path or the low noise amplifier supply voltage needs to be clean, right? So one way to clean up this is to stack an LDO, cascade an LDO at the output. Now if you have an LDO, the final output remains the same. So LDO needs a dropout. So DC-DC now should supply 2.5 plus 300 millivolt, so that the 300 millivolt can be the dropout of the LDO, and the DC-DC will now supply 2.8 volt. So you can now see that we are introducing more complexity, but this is giving us reasonable efficiency and reasonable output voltage ripple. Okay, while we might be okay with it, then we decided, okay, let's think through some more optimization and then say, why not have, because all of these are, let's say, low voltage DC, why not have one low voltage DC-DC and then run multiple LDOs on this? Okay, so that came to this part where we said, let's put one low voltage DC-DC and then have 3 LDOs running on this DC-DC. Similarly, another LV DC-DC and then put another LDO. Now, why did we have partitioned this way? Because you can see that the currents are 150 milliampere into 3, about 600 amperes here, and then approximately 1 ampere here, right? So you can see that we kind of split the energy budget into half and half, and that's why the LV DC-DCs could be operated similarly. Now, when we look at, I will come back to an option 5, where we split this now into 2 chips. Instead of one single chip, we had to split it into 2 chips because we were not meeting the temperature requirements now. While the architecture was optimal, we were not meeting the 105-degree junction temperature. And I'll show the math a little later. So that's why we had to split this and then say, okay, let's put a 2-chip solution where the first chip gives me 3 LDOs with 1 DC-DC. The second chip gives us 1 LDO plus a DC-DC. So a detailed PMU choices are all here. So let's say option 1, 2, 3, which are purely DC-DC plus LDOs. You can see that the junction temperature was going to 155 degrees C. So here, option 3. So this is not acceptable. We want the junction temperature to be limited to 150 only. That's why we had to split this into 2 PMICs, PMIC 1 and PMIC 2. Now you can see that the junction temperature, maximum junction temperature that can go is 118 and 120, which is good. You have more margin there. And also in terms of the architecture, you can see that the 2-chip solution for this PMIX was actually helping us to kind of trade off between output noise, efficiency, the number of external components, the IC junction temperature, cost, and PCB size. Right. So this was our best trade-off. So we went with a 2-chip solution, and now the overall architecture would look something like this on the next page. So you have the entire application that we showed is a dotted black line. The first chip had 1 high voltage DC-DC and then supplying 3 LDOs. And the second chip had 1 high voltage DC-DC supplying 1 LDO. Right. So this was our architecture concept, which is meeting all our requirements. Now the question is to design these LDOs. Okay. So before we go on to this, it's important to understand there's a combination of DC-DC and LDO are called as hybrid regulators. So this is a cascade of switching converter and linear regulator. So the efficiency of an LDO is output power divided by input power. So it is output power is VLDO into ILDO, and input power is VDC-DC, because this is the supply voltage for the LDO, into ILDO plus quiescent current. So quiescent current is typically small when you're designing, hundreds of milliamps based LDO. So you would see that approximately the currents would get cancelled out, and you are left with the ratio of output voltage to the input voltage as your efficiency. Now the efficiency of DC-DC converter is a little more complex. The numerator remains same because this is the output power of the DC-DC. You have VDC-DC into IO, but then the total power dissipation or power wastage input power is related to it can be split into multiple components. So this is the output power. This is the first term I square R on is the conduction losses of the of the pass transistor. Then you have switching losses because the power MOSFET needs to be switched from on to off. So you have the gate capacitance that's getting switched at a certain frequency, which will give rise to switching losses. And then you have an external recovery diode conduction losses on the bottom side. So whenever you switch off the power MOSFET, the inductor current will come through this diode recovery. So there's going to be a loss because of this recovery as well. So now the system efficiency is the product of LDO efficiency into DC-DC efficiency. So this is NLDO into NDC-DC. And when you multiply both and do some math, you would end up with a formula like this. Here you can clearly see that first of all, the R-on needs to be made sufficiently small so that your loss can be made small, and higher the VDC-DC, poor is your efficiency. So you would want to always have the VDC-DC to be low because it's in the denominator, so your efficiency will improve if your VDC-DC is small. So system efficiency increases as VDC-DC reduces. So how about making this adaptive? So this means, can I make my VDC-DC adaptive based on the load current? Okay, this is where we came up with an idea of adaptive dropout. Okay, so the overall architecture looked like this in terms of blocks. We had a V supply voltage, which was supplying to a DC-DC converter. It's a high voltage DC-DC, and the DC-DC also needs a band gap voltage. So we get a trimmed band gap reference and we convert into a high side reference. This is supplying the DC-DC converter. The feedback resistor divider is regulating the output voltage. So this generates the DC-DC output voltage, which is now supplying each of the LDOs. Okay, and this is the LDO that you see. It's an NMOS LDO. As you can see here, you have the band gap voltage getting connected, and based on the value of the resistor divider, the band gap voltage gets multiplied with the scaling factor, and that gives you the LDO output voltage. And the NMOS gate gets regulated by this gate driver, the amplifier, to maintain the output voltage at the required level. And you're having 3 LDOs for this. And with the DC-DC converter, simply if you look at DC-DC converter, just focus on this part on the output side. Okay, just for a minute, just focus only on the output side. So all the DC-DC converter does is to identify when to switch off the pass transistor and when to switch on the pass transistor. Okay, so initially the DC-DC output is 0 because capacitor is discharged. So you would charge the capacitor. So this means the power transistor will be turned on. So the current will so because now because switch is on, the inductor sees that inductor left side terminal will be at V supply and right side terminal at 0. So what happens when there is voltage across an inductor? V is equal to L di by dt, right? We all know this for an inductor. So this means a current in an inductor is integral of V by L into T into dt. So with the given time for a fixed voltage, the current builds up in an inductor. So you see that the inductor current will slowly start building up with respect to this equation. Okay, so now the current is increasing. It's fine. It's charging the voltage because the current now charges this capacitor from the inductor. So the capacitor builds its voltage. Right, all good. Now, once this reaches the regulation point where you want to maintain the VDC-DC, now you don't want to charge this anymore, right? So the power MOSFET shuts off. You turn off the power MOSFET. So the gate is pulled high because it's a PMOS. Now what happens is that the inductor current cannot change instantaneously because inductor current is in this direction. And while you shut off the pass transistor, the inductor current cannot change. Now what will happen now is simply that the current will remain same, but it will now suck the current out from the ground on the reverse path. And the Schottky diode that is there, for some circuits you have this low side NMOS also inside the chip. You can build an NMOS transistor inside the chip, but the concept is same. So you have the current in the inductor cannot change. So once the power MOSFET is switched off, it will suck the current from the ground. So you would now see that the LX voltage now goes below ground to below, let's say, minus 0.5 or 0.6 volts. And so now you can see that the current decelerates because now the voltage across the inductor is now negative. Is minus 0.6 on left side and right side is VDCDC. So now the current slowly, so you can see that the inductor current, when it reaches peak, when you shut off, now it slowly starts ramping down. Okay, once it ramps down, the voltage, and when you have a load, it is discharging this capacitor, so the voltage goes low. Again, if the voltage is lower than the required voltage, you turn on the power MOSFET again. So, and again the inductor current increases, goes to higher voltage, then again you shut off and so on. So this is how typically a DC-DC operates. And all the circuitry on the left side is basically to decide when to turn on and when to turn off, right? I don't want to go into detail of this, but the whole concept is about DC-DC is to understand when to turn on the transistor, when to turn off the transistor. And you need to do it reliability. There's still a feedback circuit here. You have to do it reliably. Okay. So what we have picked here was an asynchronous architecture where because it was compact with a small external photodiode, and this is a simple hysteretic control. So we are looking at two voltages, over voltage and under voltage, and trying to maintain the VDCD ripple within that. Then soft switching. Soft switching indicates that you turn off the or you turn on the power MOSFET only after the current is completely zero inside the inductor. So this is called soft switching, and this minimizes the switching losses. And of course, we use some adaptive on-off timer to improve the transient response and efficiency. So this is the DC-DC architecture that we've used. On the LDO schematic, like I said, you have a simple band gap voltage here, and this band gap voltage gets multiplied by the ratio of resistors to give you the output voltage. Because the supply voltage is high enough, we had the luxury to use an NMOS pass transistor. And the nice thing about NMOS is, source is degenerated here. So this is much more easy to stabilize this LDO instead of a PMOS transistor. And, a detailed schematic of this looks like you have a first stage. So this is your first stage. You have a second stage, which is a preamplifier, and you have a third stage that is a pass transistor. There are other circuits, like as an example, current limiter circuit here, because if you look at some of these high current LDOs, right, you can have, like I mentioned, in automotive, you can have suddenly this LDO getting hard short to ground. Let's say there is a fault, and then suddenly the LDO becomes ground, right? Now you see that once the LDO is zero, your pass transistor is driven hard. So the gate can go much higher, and then you will have a lot more current that goes into this, lot more current that is driven from DC-DC. So this will burn this entire metal path. So you can actually destroy this entire path if you suddenly have a fault, right? To prevent this, we need to build some protection, and this protection is done by a sensing circuit. So the M3 transistor, which has common gate connection and common source connection, is now sensing the current in the output load. And then you build a feedback loop to make sure that to kind of limit the gate. So what this loop will do is, to just make sure that, you are regulating the V drive so that it does not exceed a certain point. So this will limit the current. And of course, you can see that there are R3, C3, which is a pole zero compensation here, and R4, C4, which is giving you a zero to stabilize the LDO. Okay, so this is basically the architecture that we've used. So it's a fail-safe design, and we have a soft start to avoid high load current for DC-DC. And then we have a short circuit current limitation. So all these design mechanisms need to be built into the design so that you are robust in the application. Okay, and what is an adaptive dropout here? Let's take an example of a DC-DC converter, which is giving you a fixed voltage, and you have a linear regulator, like an LDO. So normally the dropout of the LDO, which is the difference between input supply voltage of the LDO and the output voltage. So this is called the dropout. So this is decided based on the peak load current. And in 5G transceiver architecture or some of these loads, right, it is not always operating at peak load current. So we can maybe reduce the DC-DC lower, because you remember, right, the efficiency improves when the VDC-DC is low for the system from the math, right? So when there is the current, output current is small, we can reduce the current. When the output current is peak, then you can go back to the original value. So you can adapt the VDC-DC voltage based on the LDO dropout. And this is what is done in an adaptive hybrid architecture. And these are cadence simulation results, where you can see that for different supply voltages and different loads, you can see that for a conventional dropout, the efficiency in a lighter load condition, the efficiency improves. The output voltage is reduced, the pink graph, and and at a peak load, both graphs give you same thing, adaptive dropout and conventional dropout. Whereas for lower load currents, the conventional dropout is able to reduce the VDC/DC voltage, and that gives you a improved efficiency. So this is the layout snapshot of the PMIC 1. So you can see that the DC/DC power transfer is quite big here. It's pretty huge. So as the cadence, we use the cadence virtuoso to do the layout. And you have these three LDOs here, LDO1, LDO2, LDO3, and some clocking circuitry here. And we sent it for fabrication, and then we got the silicon back. And what you see on the right side, this is the actual chip photograph. It's an X-ray photograph of the PMIC. So you can see the DC/DC and these small wires that are hanging here that are connecting are basically the bond wires. So some of these all of these are bond wires that are getting connected. So this is the chip snapshot, and we were able to do the design within about 3.2 to 2 mm design. And this was also sent for packaging. And what we eventually got was a die. So your die here is getting bonded onto the package through this gold wire. So you can see these small tiny wires here. If you decapsulate the package, you can see that this is the die, and then you can actually this is how it is connected to the external pins, right? So the validation was a big challenge, because when you want to test a circuit at 150 degrees centigrade, and you have these external inductors and capacitors, some of these do not, the external components cannot withstand this temperature. So we need to have a validation board that you see on the left side, where this is the IC, and you have some connectors here and also some capacitors, external components here. Inductor is on the back side of the PCB. And for the temperature characterization, we built a board like this, where you have a socket, and all the components are on the rear view or on the back side here, whereas only the socket and the DUT is on the front side. So you can also see this on the top, right? So this is the socket, and then you place this tiny DUT here, close the socket. So the socket with DUT is there. Now around this, you can place a thermal insulating rubber, so that only the DUT sees the higher temperature, and we can characterize this. Everything else, including the external components or the Schottky diode, all of them sees a much lower temperature, so that we can test the functionality of the IC only. And of course, you can use this, you can put this entire board that you see here on top below this thermostream, and thermostream you can control the temperature. So that is how we were able to characterize the DUT and still maintain the external components at their limited temperature rating. And the validation bench setup, we had a lab view here on the PC, and through a GPIB cable that you see here, we were able to control all the instruments to give the supply voltage, give the load currents, and also control the thermostream for the temperature step. Okay, this was our validation bench. Okay, so what did we measure? So we could see that clearly the x-axis of all of these curves is load current. So load current going from 0 amperes to about 450 milliampere, and y-axis is the temperature efficiency, not temperature, sorry. Y-axis is the efficiency of the power converter. Now you can see that the light gray lines are DC/DC efficiency and total efficiency when there is no adaptation. And if you adapt the DC/DC adaptive bias, then you can see that the bold lines are giving you a better improvement over the conventional value. The peak remains same, because at the peak, the dropout should be same as in the both cases, conventional case. But as you go down with the LDO load current, you will see that the efficiency improves when you adapt the voltage. And this is tested at 6 volts, 12 volts, and 18 volts room temperature. And then for a fixed load condition, we did also an entire temperature range sweep of efficiency. So you can see that for 95% of the loads, we are quite good in terms of the efficiency. Okay, so how do we compare the fixed dropout to adaptive dropout? So you can see that when we go to a lighter load condition, like 10 milliampere, we were getting 95.3% efficiency compared to a conventional dropout of 89. So this is comparing our own design. The same design, when you do an adaptive dropout, it certainly helps to improve the efficiency. and also, more moderate load and light load conditions, we see there is an improvement here for the overall system efficiency. Now, we also tried the benchmarking this with respect to existing DC-DC and LDO circuits available in literature. And you can see that this was the first work that was reported all the way till 150 degrees centigrade. And the DC-DC efficiency, system efficiency, the load regulation, system ripple were all very comparable, and the efficiencies were kind of better as well. So the present work is the first hybrid voltage PMIC, which has a wide input supply range characterized up to 150 degrees centigrade. So this is one of the unique things about this work. Okay, so what was the goal? To design an integrated generic PMIC solution which can work up to 150 degrees centigrade. And what we could achieve is this. This is the actual photograph of the PMIC, the rears, the package, rear and front view. Okay, so that's it from on the presentation side, and just wanted to also talk about this initiative that we have. So we have co-founded this this venture called Mozart Labs, and this is a program. This is a professional diploma program where we from Mozart Labs are partnering with IIT Bhubaneswar to run this program. The course, it's an online course for 1 year, mainly targeting third year and fourth year BTech students, and also early MTech students and early industry professionals who want to move into semiconductor core jobs. So this course will be taught by industry leaders, IIT alumni, and IIT faculty. So it's a 1 year course, and more details are available on the Mozart Labs website. So the goal of this would be to complement the university education, and then really it's an online program where the classes will be in the evening for the students, and we are confident that at the end of it, they will be industry ready. They'll be able to design ICs, and then they can apply for core semiconductor jobs. Okay, that's it from my side. I'll be happy to answer any questions or any short questions that you may have. Okay, now I stop my presentation, and then happy to answer questions. I guess we are probably okay in terms of a time, right?
Yes, sir. Yes, sir. Yes, sir.
Okay, I'm happy to take a few more questions.
Participants, so you are requested to ask if you have any questions.
So I know it's probably too much information in 1 hour, but hopefully this gives a flavor of how a practical chip design is done, which can actually, you can see the entire cycle. It's not only about designing something in computer, but really, manufacturing something, measuring it, and then proving in silicon that something works.
Yes, sir. Yes, sir. Thank you, sir. Thank you for your enlightening session, sir. Actually, your session enlightening us with your in-depth insights into the power optimization in the context of 5G, sir. So really, your expertise have widened our understanding the power optimization in the context of 5G. And really, you broke down the complexities of power optimization, or how efficiently we need to use power related to 5G enabled devices, or like 5G enabled IoTs like that, sir. So really, you have changed our vision how we need to think. So to work it on this 5G enabled device. So really, you have given a session very in depth into the level, sir. So thank you, sir. Thank you so much, sir. So participant, again, once again, I'm asking, so if anyone interested, you can ask a query. So sir actually very busy in his busy schedule also. Sir actually accepted, sir. We are very kind enough, sir.
Yeah, my pleasure. Thank you.
Sir, I'll share your mail ID to the participants, sir. If they have any question, definitely I'll forward it to you, sir.
Sure.
Sir, thank you, sir. Thank you so much. Thank you, sir.
Thank you very much. All the very best for the rest of the program. Thank you.
Thank you. Thank you, sir. So, participants, next session is going to start. SAR is already ready. So, meanwhile, our co-coordinator will share. Already, a speaker is ready to enter. Already entered. So we'll start. Madam Sandhya ma'am, are you there?
Yes, sir.
Uh,
Sir, may I
so,
go ahead?
yes, once again, very good evening to all for the fourth session on this ATAL FDP and key technologies enabling 5G. So, welcome you all again for the fourth session. So, for this session, we are having an esteemed speaker, Ram Singh sir from DRDO scientist G grade. So, now I request Sanya madam to introduce about to participant today's our speaker session speaker.
Okay, sir, sure. Good evening, everyone. I'm Sandhya, Assistant Professor of EC Department, BITS. I'm delighted to present the profile of Dr. Ram Singh, a visionary DRDO scientist with a wealth of experience and achievements. Dr. Ram Singh is an eminent scientist with over 2 decades of mastery in the field of avionics and communication engineering. He has been serving the Defense Research and Development Organization since February 1, 1999, continuing significantly to India's defense capabilities. Dr. Singh holds a BE in Electronics and Telecommunications from the Government Engineering College, Jabalpur in 1998. He deepened his knowledge by acquiring an MTech in Communication Engineering from IIT Bombay in 2006 and Masters in Information Security from Masaryk University, Czech Republic in 2019. Throughout his esteemed career, Dr. Singh has been instrumental in the design and evaluation of cutting-edge avionics systems, including Starter Electronics Control Unit (SECU), Digital Hydraulics Controlling Electronics Unit (DHEU), Engine and Electric Monitoring System (EEMS), Integrated Radio Communication Systems for fighter aircrafts, and Advanced Communication Systems for helicopters and aircrafts. Currently, Dr. Singh is actively involved in the design and implementation of e-certification systems. His area of focus extends to speech processing and coding, reflecting his commitment to advancing innovative technologies in the field of communication and avionics. Dr. Singh's contributions embody the integration of academic excellence and applied engineering, making him a valued resource for fostering knowledge and innovation in faculty development initiatives. It's such an illuminated profile, sir, and thank you for giving this opportunity. Thank you all. Madhu, sir.
Now the session is yours, sir. Ram Singh, sir.
Thank you, sir.
Thank you.
Thank you, Sandhya madam. Thank you for your kind words. And
Thank you,
thank you, Professor Madhu, for giving me the opportunity to put up my thoughts and whatever small information and knowledge I am having to share with the eminent professors and the faculties who has joined this session. Sir, am I audible, sir?
Yes, sir. Yes, sir. It's perfectly all right, sir.
Sir, I'll just share my presentation.
Okay, sir.
Sir, is the slide visible?
Yes, sir. Yes, sir.
Good evening, one and all. I have been asked by Professor Madhu to give a presentation on 5G technologies. In fact, I am working on defense systems. So, as you all know that whatever research is going on or whatever the latest field, the military will be using little established technologies, which will be probably maybe 5 to 6 years behind what the current technology going on. The main reason for this is the atmosphere or the kind of operating environment in which the military system has to work are quite harsh. So the system has to be pretty established before putting into military domain. So though I'm not an expert in 5G, but I have worked on communication systems. So if somebody is having any queries related to the communication, probably related to the 5G, I will be able to add some information. Otherwise, I am not an expert in the 5G. But still, I have little knowledge of 5G, which I'm trying to correlate with the military domain where we have used almost similar kind of technology. The challenge over here is I cannot give too technical, in-depth information for this kind of domain, but fine, I'll try to explain whatever we are using here. So here is the organization of my presentation. I'll start with the introduction of 5G. I believe mine is a 4th session. So you must have a lot of information about the 5G and its basic. I'm trying to take it from some other perspective. If it is already covered, pardon me for that. Then the key technologies which are used in 5G, I'll be talking 5G spectrum, because wave propagation is one of the important feature, because 5G is purely a wireless technology. So wave propagation plays a major role. For 5G, millimetric waves is also available, band is available. I'm not pretty sure whether in India they have started using. Probably Reliance or Jio have used something around 5G or 6G, but 6 gigahertz, but I'm not sure about 24 gigahertz whether they have deployed. Then the beam formation is one of the important feature which we use in military domain. So I'll be talking about that, and finally I'll be concluding it out. So if we see the mobile, this is the very first slide now. I'm just this I have adapted from one of the website. If you see, every 10 years there is a revolution in mobile communication or mobile technology. 1980s we had analog voice. It started with that was 1G. Then we have gone to digital voice in 1990s, which we call it 2G. And then there was a big revolution in 2000 when we started accessing the internet or data using our wireless mobile. Then in 2010 we had 4G came with long-term evolution, and we had quite a good bandwidth. And 2020 we had 5G. Basically, 5G is a huge jump from 4G, because almost in all aspects the performance is double or more than double. Now we are in 2024, so we are almost midway between 5G and 6G. Though 6G, people have started talking, and IEEE, I have received some of the mails and some of the papers which talks about the 5G technologies. Probably now, if we see the major change from 5G to 6G will be use of AI, I believe. The entire feature what has been implemented in 5G probably will be optimized or used with the higher efficiency using the AI technology. Obviously, there will be RF sensing. If you see the last slide, there's a topic called RF sensing. So probably we will have a much more sharing of the bandwidth, and there will be kind of protocol. So there was a system which was we used to call it carrier sense radio, which was being talked almost a decade back. In military domain, as I told, I'll draw the parallels of 5G with all military domain. So at present in military domain, if you see software defined radio is very prominent. We are planning, or the all the tri forces are trying to convert their conventional radios with software defined radios. So a lot of development in that field is going on. There will be what we call it smart radio, yes, but carrier sense, like where the same channel, if it is not being used, it can be utilized by somebody else. We all know that if we license a channel, the 100% utility will not be there. So some kind of carrier sense network will definitely be used in 6G, which will definitely enhance the throughput to a very good extent. Now, I'm having few slides on 5G. So what actually makes the 5G as compared to 5G as compared to 4G? The very first thing is the peak data rate. The specification for 5G is the download speed is 20 gigabits per second, and upload speed is 10 gigabits per second. The same speed in 4G is the downloading speed is only 1 gigabits, whereas upload is only 0.5 gigabits per second. So if you see, the speed here is almost 20 times high in 5G as compared to 4G. The data rate for the user, actually it's a typo, it's a user data rate. So it's approximately 100 Mbps what we are getting now with 5G, whereas for 4G it was only 10 Mbps. The peak spectra efficiency is 20 bits per second per hertz, which is pretty high. It is almost double as compared to 4G. The speed of data connectivity can be maintained up to 500 km per hour. Whereas in 4G, it was only 350 km per hour. I would like to ask at the end with all the members that what is the reason that mobility? Do we have this kind of speed available with the maybe vehicles or something where we have a mobile or something being used? And which area of RF communication will get affected with this such a high speed? And how will it have a adverse impact? So I request all the audience, if somebody can tell me in brief at the end of presentation, it will be very useful, and I will feel I am able to communicate some of the good information. User latency is specified for 5G is only 1 millisecond, whereas for 4G it was 10 milliseconds. This is another very important parameters which has been given in 5G. This also have a major impact. I would like to share some information over here. See, 4G, if I have to control some of the drone or some of the remote devices, the 10 millisecond latency is quite high. If the drone is flying at quite high speed, then 10 millisecond it may get collide or get collapse. The use of this 5G in 1 millisecond will be a reasonably good latency for me to have a control over autonomous vehicle as well as the small UAVs. So this is one feature which has been given. And the connection density has become tremendously high. It is 10 to the power 6 devices per kilometer square. And in 4G, it was only 10 to the power 3 devices per kilometer. The major reason for this connection density is in 4G, we were not going to millimetric wave. And in 5G, the millimetric wave has been enabled. So we will have a lesser, we can't transmit the same signal of the same strength for a longer distance if it is higher frequency because of the path loss. So this has given a very good advantage of using a smaller cell. Once the cells are smaller, we can go for a very high density of the devices. And at the same time, as you all know, we are talking about the 5G, which is completely based on the cellular technology. So the cell size plays a major role. It has like it can give a quality of service, and the signal level, everything is controlled by the size of the cell. That itself is a big topic, the cell division and how to create the cell in a given area depending upon the user requirements and depending upon the network bandwidth you have, the kind of license you have. So all those things, that's a very broad topic. I have not covered any much on that. I just touched upon this topic. So what are the key technologies which have been used in 5G and which were not existing in 4G? What I would like to say that it's a very smart use of the existing technology and use of few of the new technology. So the new way of deploying the new stuff, the first thing is radio access network. We all know that in wireless communication, the entire data transaction happens over a wireless network, which is nothing but radio network. So how to have access to this radio network? See, if you see in 1G and 2G, we used to have a dedicated channel for transmission and reception. But here also we will have this kind of thing, but it can be optimized, and it will be based on some computing architecture that what kind of channel bandwidth to be allocated. So all these things are very dynamic. Second feature is the ultra dense network. This is as I told in the previous slide while giving the explanation that because of millimetric wave, we can't transmit the power for a longer distance. So here in 5G, what has been used for the advantage, the cells has been made small. Once the cells has been made small, it gives the advantage of reuse of frequencies. So this allows us to use the ultra dense network. At the same time, yes, I do agree that bandwidth is also available with us for a high data transmission. But the use of higher frequency allows to do this. Then device-to-device communication is also allowed in 5G. So utilization of devices serving as a relay to provide communication with other devices. This is one of the advanced features available in the 5G. The next feature is now using the physical layer, which is communication. So here in 5G, massive MIMO technology is being used. We all know MIMO is multiple input, multiple output. So till generally we will be using 2 or 4 antennas for this MIMO kind of system, but here multiple antennas has been used. I'll be talking much with a slide on this. And millimetric wave. For 5G, 30 gigahertz to 100 gigahertz band is also available. I'm not sure about whether auctioning has been done by ITU, no, by Indian government, or is there any plan to release some of the band on this? But yes, in this band we will have a lot of opportunities to have a very high bandwidth, especially 30 to 100 gigahertz. But it comes with its own challenges as well. The third thing is the new way of running the infrastructure. See, what I could find when I was reading across the literature of 5G, everybody used to have their own customized way of transferring the data, communication, especially in the physical layer. What 5G talks about, it talks about uniformity. So basically, it does the network function virtualization. So it decouples the software and the hardware. So it could be a different hardware, but software should be portable on that, and that should allow the network function. Basically, here what they have done, they have made a segregation between the control plane and the user plane. So by doing so, they are able to optimize each plane by using software-defined network. They have decoupled, though I'm not very much expert on this, but some kind of optimization they have done by decoupling. If you see, it is similar way the way SDR works. So in SDR, I will have a common hardware, but at the same time, I will be able to port the waveform as per the application required. So it appears to be similar kind of feature where based on the user requirement, based on the user application, the application or the what I say user plane can be configured, and that will allow to have a better service quality. Then network slicing, utilization of single infrastructure to provide different kind of independent logical network is one of the important feature which is being utilized in 5G to have a better services. So this was all about the technology, how 5G is using all sort of things to have a better performance, better bandwidth, better I should say throughputs. Now, if we see the bandwidth which is being used by 5G is the first one is the low band, which is sub 1 gigahertz. That is also available in 5G. Then we have mid band 1 gigahertz to 6 gigahertz, and then finally we have high band, which is above 6 gigahertz. So if we see that the most interesting part is 5G spectrum, which is shown in the green color here from 6 gigahertz to 24 gigahertz and beyond that. So this is what the millimetric wave, and where we will have a high frequency as well as high throughput available. But this particular band operation of 5G will have its own challenges, which I will be talking in the next slide. Here, basically, the spectrum will applicability with the bands. So where and all the spectrum is a small comparison, which I have taken from, I believe, from the Ericsson website. So what basically it has been told that if the band is less than 1 gigahertz, the enhanced mobile broadband. Basically, this talks about the the bandwidth which we are able to exploit in our mobile. So it says the advantage is the one less than spectrum when we are using less than 1 gigahertz. It got a long range, but the spectrum is not available. It's highly congested. This can be used for all three kind of services. Basically, the 5G is known for its enhanced mobile broadband, massive machine type communication. Basically, enhanced mobile broadband is basically from the consumers like those who are using the mobile. Massive machine type communication is primarily for the sensor networks. So if you have some sort of say smart city where we are collecting a lot of data through the sensors, through the 5G network, so then this kind of thing will be applicable. And then ultra reliable and low latency communication, which is intended to be provided by the 5G. This is purely for like autonomous vehicle and UAVs and some sort of control application. So if we see that less than 1 gigahertz, it can be deployed for all these three kind of application of 5G. Whereas the band between 1 gigahertz to 6 gigahertz, it's a wide band, low availability of spectrum. Actually, in this band, even the military band is also available. So this band is not so freely available. It's good for us to give a good bandwidth. It's the best actually, and it is good for the other two application. But if we see above 6 gigahertz, it's an extreme wideband. But the major challenge over here is the short range, mainly due to the path loss at higher frequencies. Yes, this band can be used primarily for the enhanced mobile broadband. Uh, Till there's no still maybe study maybe going on that this band is not very much suitable for machine type communication, and this probably may not be used for ultra reliable and low latency communication. It is not possible, the primarily due to multipath loss in this particular band and the attenuation. So this is a brief summary that whatever band is available in which different feature of 5G it can be utilized. It's summarized over here. Now, as I told, I'm very much interested in any propagation above 6 gigahertz. So if we see the millimetric wave propagation, the main reason is this is the range at 100 meter. If we see at 100 meter, as the frequency increases, the attenuation goes up. At no a range of 1 kilometer, we will have something around 110 dB, and maybe at the range of 10 kilometer, we'll have something around 130 dB, and at around 70 gigahertz, we will have something around more than 140, 145 dB attenuation. Actually, this how does this affects? No, if you see the classical formula for the path loss, which start with minus 171, which is minus 171 dB plus know your 20 log of frequency, 20 log of delay, and 20 log of bandwidth is a classical path loss formula, which is primarily governed by your thermal noise. So the thermal noise is the one which controls our attenuation of the path loss. So if my signal is below than my thermal noise, I will not be able to detect it. So basically, the major problem with the millimetric wave propagation is a path loss, which has been demonstrated over here. So we will not be able to communicate for a longer distance, because what I feel, the very good sensitivity in this millimetric wave could be something around maybe uh, as low as minus 90, minus 95 dBm. So whatever power we push, probably getting a range of more than a kilometer will be very, very difficult. So this has a direct parallels with what we are very, very careful in the military domain for the communication. Now, the second problem is a shadowing effect. As we go with a higher frequency, that what we call the diffraction or a Rayleigh effect will not take place, and the shading will be very, very prominent in case of millimetric wave propagation. So if any, like this is the top floor and the ground floor available. So in this area, if there is an angle, this area will be dark area where we will not be able to receive the signal. Whereas when we are transmitting in the lower frequency band, due to Rayleigh effect or multipath reflection, probably there's a possibility that we'll get a little weaker signal. Then the another major effect with the millimetric wave is the absorption by atmosphere. So the red curve here shows the absorption at the altitude of something around 900 9 kilometer altitude, whereas the green one shows at the sea level. So we can see that as the frequency goes up, the atmospheric absorptions is also increased, and it go as high as, if we see gigahertz, something around 6 gigahertz. It is a very high, something around 10 dB per kilometer. So if we see a distance of 10 kilometers, almost 100 dB loss is there. So we will not be able to have a very good communication. We will not be able to receive the signal for a longer distance. But this is a very interesting curve, because if you see that at 8 and 10 gigahertz, we will be 8 and 9 gigahertz, we will have a uh, better better range because of the non-absorption by the output. So these are the few atmospheric effect which has to be considered while deploying the frequency in the 5G, and the 5G network will definitely be taking care of all these aspects. The next technology which has been used is massive MIMO. So MIMO is basically in a wireless network that allows transmitting and receiving of more than one data signal simultaneously over the same radio channel. That's the classical definition of the MIMO. Ordinarily, we used 2 or 4 antennas to have either code division multiple access or OFDMA kind of signals. But in massive MIMO, which is planned to be deployed in 5G, it can use tens or hundred of antennas. Actually, 96 to 128 antennas are already demonstrated by a few of the companies like Huawei and Facebook. They have shown the MIMO system utilizing 96 to 128 antennas. Now the question arises: why we are going for this MIMO kind of things? In fact, in multi-domain, we are using it very extensively. The answer is here. Basically, these massive MIMO systems will be used for beam forming. The beam forming is having its own advantage. The first thing is, if I am doing the beam formation, I will have a directivity. I will have a directional gain. So I will be able to get a better range. That's the first advantage. Second advantage, it will have a lesser interference in the adjacent signal or adjacent frequency, which is being transmitted to another device. So it's a win-win situation using this MIMO kind of system. But what I am showing here is a one-dimensional MIMO system. But now the talk for the 5G is to have antenna or MIMO system which can have a 3D beam forming. So say for example, in an apartment, there are 2 different users which are having a different need or different kind of subscription. We can have a separate beam formation, and with less power, we can transmit the data to the two different floors with a different speed and with less power without interference. So this kind of feature is being adapted or built in 5G, which will have a long-term impact, and it will be say it may not be for one particular user, it could be for a group of users as well. So this is very advantageous condition by using the 2-dimension MIMO system. I think the title was sorry, by mistake it has come. Now this I thought though this appears very simple. No, there's a very how basically it is done, because being in RF field, I just thought I'll put a one slide that how the basic beam formation happens. If you see here, there are multiple antennas available, and each antenna will have a phase shifter. So this phase shifting value can be controlled by any microcontroller or microprocessor. So depending upon the direction of the beam it is required, I can adjust these phase values for that particular frequency. And then when the carrier signal is generated or modulated signal is generated, and after it comes to the transmit after amplification, it will be able to transmit the entire antenna array system will be able to transmit the beam in a particular direction. Actually, this feature is extensively used in military domain for phased array radar, which we call it active antenna array radar. So, this is what the technology which is being used in 5G extensively for providing a very specific kind of feature uh, to have less interference. But this is being used in military domain extensively. I'll show some of the diagram. So this is the aircraft radar which uses the beam formation technology. Actually, this earlier, if you see the mechanical scan radar, we used to have 2-dimensional gimbal, and we used to have kind of what I say, a discon kind of thing, where we used to transmit the signal and it used to do the scanning. But now there's no mechanical movement required. The entire beam, this radar can do track, can do a search, can do a scan by using the beam formation technique. And the principle is exactly same. We will feed the RF signal, and with phase shifter, which will be calculated based on the direction the beam has to look, and then the beam will be formed. In fact, even the beam width and its parameter also can be controlled with this. This is what I am talking about, the fire control radar, which is fitted in an aircraft. And this is another radar. If you see that on the back of the aircraft is also beam forming radar, which can look into entire 360-degree, except some maybe 10-degree in the nose and 10-degree in the tail side. It can do a surveillance. So this is also a kind of phase array radar which uses the beam formation. So what I would like to communicate here, that beam forming technology which is being adapted in 5G to have a very specific application is very stable and widely used in the military domain. Another application, very interesting application of this beam forming is phase interferometry, which we use extensively in the military domain. Uh, if you see that when I am flying, I will have some systems which will tell me that enemy aircraft is coming from which direction, at which angle. So basically what I will have some kind of antenna array either at back of my aircraft or at belly of my aircraft, and that will be working on the principle of phase interferometry. So basically here I am showing that antenna 1 and antenna 2, and signal is coming from a direction theta. So signal will reach at antenna 2 and it will be delayed by some time delta, and it will reach at antenna 1. That delta is nothing but a phase. So the delay in the delay in the reaching signal, if time I knows, I will be able to convert into the angle of arrival. So this is basically what I will be doing. I will be measuring the phase difference between these two signals. And once the phase is known, that will be converted into angle of arrival. So this is one of the very interesting application of antenna arrays, which has been used in military domain. So this was all what I was projecting about the 5G in brief. Now this is the conclusion slide. I am sure I've not gone very fast, but we will have little time for the discussion. What I would like to conclude that the technologies used in 5G are continuously evolving. Now, I have been told by Professor Madhu that no, this program is purely for the faculty development. So I would like to dwell upon some of the aspects which faculty can ask students to design or do some practical. So a very simple thing, what I would like to say, like simulation of beam forming using the MATLAB. So they can work out some of the small implementation using either Simulink or something where the phase can be changed with the multiple antennas, and the beam can be formed, beam can be swapped. So that kind of application as a practical task can be given to the student, and definitely it will be very learning for them. Second thing is antenna pattern generation. So prediction. Generally, when we design an antenna, we have to measure its radiation pattern. But there are the models available by having a type of antenna, by having multiple elements into that antenna. Mm, There are models available which can be used for developing its pattern, its 3D pattern. So this can be another task which can be given to the student for learning. If we see that filter design, though it looks to be a very simple thing, but designing a particular filter, especially digital filter, is another challenging thing. Whether it's a no it's Chebyshev filter or Butterworth filter or any advanced filter like we have so many complex filters also available. So that kind of task can be given to them for the implementation and practicing. That can be a given. Uh, what second point I would like to conclude is that technology maturing in 5G can find application in the military domain. That's for my own consumption. Say if the system becomes very stable in 6 gigahertz to 30 gigahertz, and we have very good synthesizer and other devices, filter, amplifiers, probably those can find its application definitely into the military domain. What I would like to say, there were the time when military was leading the technology, but at present the scenario is changed. At present, the commercial market is leading the technology. If we see now, way back we used to get the mill grade components, but nowadays mill grade components are not available. We have industrial grade components or automotive grade components. So entire production for military applications are also being used these components. So there are very specific components which cannot be used from the commercial or mill grade. This is what I would like to say, that now the technology is being driven by the commercial market and the automotive market, because the volume is very high. The volume in the military domain is very less, so the entire paradigm shift has happened. There are various areas in 5G which can lead to good research topic. actually, initially I planned I will talk about the coding which has been used, like polar coding and LDPC, but I found that as a very dry topic, so I changed my mind. And in fact, to Professor Madhu, it took some time for me to confirm in that on what topic I am going to do. In fact, I prepared few of the slides, but then I found it is very difficult in a 1 hour lecture or and I'm not an expert in that. I know little thing, but not much, so I changed my topic. But yes, the error correction coding like CRC, these all can be asked students to implement in MATLAB. They can even if they take the snippet or the code from the internet, but once they run it, they change its parameter. It will be a good learning exercise for them. Channel estimation is one of the topic, because as I told, once we go to gigahertz band, no, we don't have that option of there will be a lot of reflection, path bending will not be there. There will be multipath reflections will be there, and no, we will have loss of signal at blind zones will be formed. So these and all are challenging areas where a lot of research has to be done. In fact, I will share one of the incident, like for UAV operation, we have you know telecommand systems, like UAV. There's no pilot sitting, so we have to control it from the ground, and that control data is transmitted over two bands. One is the UHF band and one is the C band. The major challenge which we found during the C band operation was multipath cancellation, and many times the aircraft was not receiving signal when it is on the runway, either taking off or landing. So what strategy has been built that, in fact, it is being followed all over the world. On ground, UHF and VHF channel will be used for controlling the UAVs. But once it takes off and it comes above the horizon, then C-band data link will start. But the reliability of UHF is much, much high. Only the disadvantage is I don't have bandwidth available over there. So I can do control and command up to 400 kilometer, 300 kilometer, but bandwidth is not available. So to have bandwidth or high data rate, we have to use C-band. But the same C-band cannot be used while it is landing. So these are kind of challenges. Probably the same thing may happen in 5G, but because the things are stationary, except the user is moving, other things are stationary, probably we can have a better adaptive solution or better fixed solution. So there are challenges. Then RF design is one of the important aspect. I'm not very sure once we go for 30 giga, 24 gigahertz and above, that amplifier, power amplifier, and its design, the PCB design, all those things will be a very challenging area. These can be studied by the students and can be given as a project to them for the study. So this is what the brief I have prepared and I have presented to you. Any questions? I will be more than happy to answer. Madhu sir, that's all from my side, sir.
Sir, thank you, sir. Thank you for your wonderful session, sir. Really, in your busy schedule, I know actually how you busy. So, sir, very grateful to you, sir. So, thank you for your wonderful enlightening session on the key technologies enabling 5G. Sir, actually, your deep explanation and actually made us to understand the concept which you have given in a easy understanding manner, sir. And even at the last, you have given some suggestions for us to do some research. Uh, Sir, actually, I have a question, sir. Sir,
Yes, sir.
actually, we are going for small cells, but when we go for the deployment of antennas or like base stations also at the other end somewhat cost effective, sir. How can we compensate that, sir?
Sir, can you repeat, sir? In between, there is a loss of voice, sir.
Sorry, sir. Actually, when we are going for some small cells, as the propagation loss is more, we are going for small cells. So for
Right.
every cells, the deployment of antennas like base stations, at the other end, it is somewhat cost effective, sir.
Yes, sir. What you say is a very valid thing, sir, because if we are making the smaller cell, probably we have to again repeat the base station and no antennas and infra. But sir, what they will do, sir, they will do very judiciously. This cell formation itself is a very in a field in itself, sir. Depending upon the user requirement and the density, sir. Based on that, they will detect the cell size. But yes, I do agree with you. Once we go with a higher, 5G and a millimetric wave, if I choose a bigger cell, I will be at the loss, sir. Probably what they will be doing, sir, cleverly. What I say, where they have a very high density user, they may go with a higher frequency band and the antennas related with that. So they will be able to provide the service, sir. But the cell which is of bigger in size, probably they will go to lower frequency bands, sir. Because the advantage in the 5G is, sir, this radio access network, sir. Here only RF thing comes, sir. At the back end, everything it seems it is using like Ethernet, some separate kind of protocol which is very much uniform, sir. So once the signal get converted into the data, then its flow is on its own, sir. So like the back end, there's a high amount of uniformity, sir. So I will not have any difficulty in connecting a 5G cell which is using a gigahertz antenna to another cell which probably using maybe less than 6 gigahertz, sir. So because back end this commonality is there, sir. So that they are going to explore, sir.
Sir, one more, sir. Actually, at that beamforming, we are focusing on changing only phase shift of the signal. So, do we need to focus on the amplitude of the signal also?
Yes,
sir?
yes. I think I have not covered, sir. Amplitude also can be controlled, sir. If I am not looking for a higher range, probably I can control. So both can be controlled, sir. Yes.
Sir, and lastly, sir, actually, how can we incorporate AI for this beamforming? Because nowadays everyone is going for AI. So, for how we can incorporate for allotting suitable power or suitable phase shift for the signal?
Yes, sir. Sir, what I would like to say, though AI is emerging and we are finding its many of the application, what probably I feel, sir, if you see AI is like if you asked me, no, earlier we had a neural network and so many things were there. So what I feel this is very advanced technology. So what they may be doing, say depending upon the requirement, I may get my model trained, sir. That at particular time, the bandwidth at so and so area, so and so direction emerges around. So the network can be self-learning, sir. And then I will give a control to it that no, try to have our own correction and try to do the beam formation on your own. So it's at present what best we can do. We can have a static, sir. We can have a time-bound manner. Say
Yes,
if
sir. The
the
condition
auto starts
change.
a particular direction, I'll give higher bandwidth. Like that, I can give. But once the AI comes into picture and it start adapts itself, generally parameter has to be changed, sir. So that control
Yes,
can be
sir.
done by AI. But the most important aspect is how does it learn? At what time, what bandwidth requirement is there, and how adaptive it is. That will be very interesting thing to know. Probably a lot of algorithms has to come in that aspect, sir.
Yes,
But
sir.
once that comes, probably yes, it is very much feasible, sir. I can say this.
Sir, thank you, sir.
Sir, I have
Participants.
query. Hello.
Please, sir.
Uh, Sir, am I audible?
Yes, sir.
Yes. Sir, like we have two types of HC-RAN, basically heterogeneous and homogeneous. So how does it differ, homogeneous RAN and heterogeneous RAN? In what sense they differ?
Yes, sir. Though I don't have that much, but what I say, the radio access network is primarily, see, if I am having bandwidths available, maybe a different frequency band. So, homogeneous radio access network, probably I will be, it again depends upon the kind of device, sir. So, for example, I was just seeing now, like your device can have that conventional 2G kind of signal access also, and you can have a 5G also, sir. So then it becomes a heterogeneous device which needs like what we call it, sir, like SMS kind of facility. It's just URS or it just went out of my mind. So your device can have no two different kind of possibility or accessibility. So then if my network gives me both the band access, then it becomes a heterogeneous RAN. My device is able to do. But if I'm operating primarily on a single band, it's a non-homogeneous. It's a homogeneous RAN, sir. This is what I can say, but I have not much idea about how exactly they are doing. I was reading somewhere my device can have two bands, so then it becomes heterogeneous. But that my network should know that my device is capable of doing that.
So, sir, band means in this, you're talking about this in band, on band, like if both the devices are within a network and one is within and one is out of coverage and both are out of the coverage. Is that band you're talking about or some other?
No, sir. No, sir. I'm talking about the two different frequency bands, sir.
Yeah, so that's what two different frequency
Two
bands,
different
like
frequency.
basically which covers some coverage area, and there will be some
Yes.
cellular
Yes.
device and one in some other frequency band kind of.
Yes.
Sir, I
So,
have one more query. Like in resource allocation, whether it could be cellular users resource allocation or a device to device resource allocation, like basically we allocate power and channel to the cellular users, like when they are close to each other, then they act as a D2D devices. So how do we allocate these resources using some machine learning algorithms or like some AI techniques? Because for that we require some data set, and we don't have any such data sets available. And now, like beyond 5G or 6G, we are talking about AI driven technologies to be emerged in this networking field. So how we can relate and how we can do the work, like using this machine learning things like reinforcement learning or some any other learning.
sir, what I would like to say, sir, as you told that no resource allocation, the power and the channel is the two most is the important thing, sir. Which governs almost every aspect of my accessibility, especially radio accessibility. Sir. So you're asking, sir, how to use it now, AI and ML. What I would like to submit, sir, at this moment, I have not come across any of the algorithm or any of the paper. Though R&D is going on, but probably people have not yet published that kind of algorithms or the research paper. But what I would like to say, sir, for algorithm, this is what purely my understanding, sir. If you have, no, you must have studied the adaptive signal processing, sir, or ASP, advanced signal processing. There we had talked. There was some talk about adaptive signals. So there, the thing is, sir, if we club that kind of where the most advantageous part over there is none of the parameters are fixed. Every parameter is being adapted depending upon the signal. So now here, those parameter, if I can change based on some huge amount of data which I have gathered, say if you have to optimize the power control you want to do through the AI, sir. So you should have a good amount of data monitored depending upon how the power requirements are there for that, depending upon the range or in that particular cell, maybe weather or depending upon beam formation. It again depends upon how you are deployed. So once you have a good amount of data, probably you can optimize, extract those parameter feature based on the learning. There are basically if you see AI algorithm, they will be continuously learning. That's the most advantage part. So in a first cut set, if you provide them and then start adaptively updating or self-learning kind of feature, then it is possible to do that. I'll give an example, sir, though probably I'm not able to correlate. I'll give an example like, sir, when I have to make a AI algorithm for my speech to text conversion, sir. So what I will be doing, sir, I will be having some initial data available of some say 10 users, and I will train my model, sir. So these model, if you see, sir, basically it goes with a hidden Markov model or Gaussian Markov model where learning will be there in each path. Some probability assignment will happen, sir. So once it has been done, then I have to verify my output and give an input. Okay, these were the error. Give again another set of data. So how this learning happens slowly that it becomes a completely AI kind of thing. So further, if any error happens, we have to just give an input that this was erroneous. The system will automatically correct itself to try to optimize. So probably the similar technique, similar scheme can be done for power and channel. Though at present I don't have a specific answer how to do it, which algorithm to be used, but some sort of this is what is my feeling, a gut feeling based on the whatever I have read, that algorithm can be made for this kind of things.
So one last query related to D2D. Like in D2D communication, we are having a problem. Like we have a problem like interference mitigation. We have to mitigate the interference ratio. So how can
Yes.
we mitigate that interference ratio in D2D so that it could be an effective communication? What could be the possible solutions to mitigate the interference?
So device to device communication, can it be a little more specific? Like if we are using Wi-Fi kind of device, is it with respect to that, sir, or is it with respect to directly
Like,
using NFC kind of thing, or sir, Bluetooth point to point, sir?
no, sir. I'll tell a scenario. Like in a closed cell, like
Sir.
of 500 meter or whatever, we are having a base station and we are having some cellular devices, mobile devices, and in
Okay.
which two devices are placed very close, so that like their proximity, like they are very close to each other. So instead of communicating via base station, by bypassing the base station, these two devices are communicating each other. So in this case, like the resource allocation, like again it will be like let's say there is some other device, cellular device, which is not in D2D mode, but that device's power and channel, ये whatever the सब carrier जो है वो और पावर के साथ ये दो अगर बेस स्टेशन के नियर में जो भी D2D डिवाइस है, तो अगर इनसे इंटरफेरेंस होने का चांसेस है, तो ये कैसे कम हो जाएगा? जैसे इंटरफेरेंस, हाउ दिस इज अ सिनेरियो.
Sir, I'll give little input. Like apart from the control channel, I think base station will allocate different channels, sir, for these devices, mobile devices. But still, I will assume the scenario what you have given, that uh, say the two devices which want to communicate with each other through the base station, and base station has identified they are in the same cell. And as per the 5G, it has asked me to maybe dedicated channel something between device to device communication, right, sir? And there's a third device which is directly talking with the base station and probably generating a lot of noise and power, right, sir? Am I, my scenario is correct, sir? Sir?
Okay, okay, sir. Thank you.
Gautam, sir, is it correct understanding?
Yeah,
Sir,
yeah, okay.
I'm coming to the answer, sir. Now, what best possibility is there if device one and device two, if we have reduction in my signal strength, or there is a noise level has gone up, probably one option is over control channel. I can ask base station to change, or I can, if I am autonomous, I can communicate to device two to change over to another channel. That's how I will be able to do, sir. Apart from that, I have no other way or means if my interference has gone in my in-band signals. In-band signal is very difficult to get rid of, sir, because this is purely digital communication, and any bit loss will definitely lead to packet loss, and then it will have a loss of communication. So the best possible way is to in a device we can monitor my algorithms, AGC algorithm, that signal is becoming poor or weak. The way we do in cell handover and takeovers, that it happens. So I can definitely ask communicate device to go to another channel and then mitigate it. I hope I have understood the problem and try to give the answer, sir.
Yeah, okay, okay, sir. Thank you.
Sir, I have
Another
one
few
query.
things in RF, no, sir. Something we can do in RF, sir. We can have restrict the bandwidth, input bandwidth, or I can go with lower data rate. But I'm not pretty sure whether these devices will be able to do that, sir. Sir, please go ahead, sir.
Sir, I have a question.
Yeah, please, sir.
Sir, how that 500 kmph speed and all supported? Because
Yeah.
the number of base stations are going to be increasing, no?
Sir, basically, that's what I have put the question, sir, in beginning. Basically, in military domain, sir, we had a major problem because we always have a speed of our aircraft are generally say more than 1,000 kilometer per hour, sir. So we had very major issue with establishing the connectivity. I'll give little brief, sir, what exactly happens. The main impact will be my Doppler and carrier, sir. When I'm flying at such a high speed, my receiver and the carrier, it will have a Doppler shift. and because of Doppler shift, my entire baseband will shift, and I will have higher bit error rate. So my all RF system should have capability to make sure that even with the Doppler shift which is coming because the speed of the vehicle should be able to compensate, and I should be able to do the proper decodings.
No, apart from that, at that frequencies, how many base stations are required? That is also it's
No, sir, the speed is basically once you are connected with one base station and you are moving maybe for a shorter distance. I'm not talking like 1 hour we will be moving in the same cell. I'm going with very fast speed, sir. Maybe a small UAV flying or something is moving, sir, which is very high speed in the same cell. So I should retain my connection with the base station, sir. That's how the thing is.
Sir, my point is, as you said, let us say some aircraft kind of thing is flying, then like typically at what frequencies it will be communicating? Again, millimeter wave, or it will be something else lower?
Sir, any frequency band, whether VHF, UHF, right? Anywhere we will have that Doppler effect, sir. So basically, if you see, sir, what happens now? If your base station is stationary and a vehicle is moving close by, so what will happen? I will have a very less effect, and then I will be able to compensate it in my design, sir. But what happens as I am designing my system to handle a higher speed scenario, then I should have that resilience or design in my RF system or in my decoding algorithm that this Doppler should be compensated, right? This Doppler effect should be compensated. So that's how now design in 5G, they are improving that, though it has not been talked about how they have done, but the specification given is that base station should be able to communicate with the device which is moving at a peak speed of 500 kilometers per hour, which is a very it's spec, sir. But whether the real system is able to do it will depend upon the design and the deployments. Where the same speed requirement for 4G was only 350 kilometers. Apart from that, sir, there will be multipath things also will come into the picture, but that's I'm not taking its effect as a major. The main effect happens because of Dopplers. Sir.
Or will it be handled by OFDM, or we need to go for OTFS or any other modulation scheme for that?
Sir, any whether, sir, you use CDMA or OFDMA, sir, anyway finally carrier is coming, sir. And that carrier again I have to beat at my receiver with the carrier and bring to baseband and then do whatever IQ, and I have to do the demodulation. The main issue happens in all my lock loops, sir. If my Doppler comes into the picture, and then finally, so that will go little, it will become more like RF and no the synchronization thing, but it is challenging, sir. That is where the effect happens, sir.
Thank you, sir.
Sir, Madhu, sir.
Yes,
Actually,
sir.
this was
Thank
purely RF. I thought
Yes.
no, maybe some offline if some discussion can happen. No, subsequently.
Yes, sir. Yes, sir.
I'll definitely be more than happy to answer the query. If you can send on the mail, no, I'll give some of the scenarios where we really
yes,
had a
sir.
problem. Sir.
Sir, yes, sir. Yes, sir. So really very thankful, sir. Actually, just even though you are very busy, so you very kind enough for accepting our invitation and delivering a talk on this, sir. So really, your knowledge so made us to deep understanding or in a clear understanding manner about this. Yes, very thanks, sir. And even you are patiently answering the questions, sir. It's very grateful, sir. So
The
thank you,
questions are
sir.
very
Thank you
interesting,
so
sir.
much, sir. Thank you, sir. Thank you so much, sir. So in future also we'll try to plan one more any such type of program, sir.
Fine, sir. Most welcome, sir.
Sir, thank you, sir. Thank you so much, sir.
I request you, sir, to give me the topic, because if you leave me open-ended, no, it will be challenging for me. If you give me specific, my no study and little research can be focused, sir. So 5G is a
Yes, sir.
very vast topic. Once I
Yes, sir.
started doing and started looking into it, it's a vast topic. A lot of areas are there in that, sir, which is there for learning.
Sir.
Especially coding, there, I told you the polar coding and LDPC
Yes,
coding.
sir.
Very interesting, sir. Because block codes and all, no, sir, encryption, security, so many things comes into the picture. So we don't know. Like tomorrow, the security also that encryption and also will take place when it comes to UAV and autonomous vehicle. I should not be able to control somebody else's vehicle. I should have authentication, authorization. All these things will also come into the pictures. So it is
Yes,
really
sir.
very emerging field and very lot of technologies are involved in that.
Sir. Thank you, sir. Thank you so much.
Thank you, sir. Thank you, all the professors and teachers who has participated and heard so patiently. Thanks for your time. It was pleasure interacting with you, all of you. Thank you very much.
Thank you.
Thanks. Good day, sir. Shall I leave, sir?
Yes, sir. Yes, sir. Yes, sir. Thank you. Sir.
Thank you. Thank you, sir.
Thank you. Thank you. So participants should try to fill the Google form, which you are going to get it in a short time. So though most of you are filling Google form, but most of you are not joining. So actually we planned this Google form due to some network failures, some participants unable to join. So please try to utilize this opportunity and join each and every session. So meet you all tomorrow. Thank you. Thank you.